All right, folks, just going to do a quick review over the notes that you should have taken already on Tuesday. I broke this slideshow up into two parts, so I'll be making the video on the other section, the last, 10 or so slides. Anyhow, this is about naming chemical compounds. You guys, as the student, are going to know how atoms form ionic, metallic, and covalent bonds, mainly ionic and covalent. Okay. Talk about metallic a little bit because it's in there, but mainly for naming and writing formulas, it's going to be the two main types, which is ionic and covalent. Okay, you are going to be able to, or expected to, name ionic compounds containing main group or transition metals, covalent compounds, acids, and bases using International Union of Pure and Applied Chemistry rules, which short for all of that is IUPAC. Those are the rules we use for naming. There's other naming schemes out there, but that's what we use. And those are our, we call that nomenclature rules, okay, for naming. So let's get to it. So let's see what you know already. You should know about ionic compounds. Those are the compounds that have a metal with a non-metal in it, and electrons are transferred, right? You have a cation, which is from the metal, positive cation, and a negative anion from the non-metal. Put those two together, you get an ionic compound. All right. When you test these in the lab, you will see that any ionic compound has a very high melting point. Okay. And when it is dissolved in water, it will conduct electricity. If it's not dissolved, it's just straight powder, it's not gonna, no magic's gonna happen in terms of conducting electricity. It needs to be dissolved in water, so you get those ions floating in solution, create that current for the electrons to move across it to conduct. Elements have big differences in electronegativities, going back to your rules for a periodic table. Some of those trends that you needed to know. Remember, fluorine is the most electronegative. Francium is not. It's the least electronegative. Still, both of those are very reactive, but for different reasons. Okay. So we always start you off with binary compounds, meaning there's two things in it, just two. Okay. And one of those is going to be a metal, and one of them is going to be a non-metal. It doesn't tell you the ratio. The ratios could be 1 to 3, 2 to 3, or 3 to 2. But as long as there's just two different types of atoms, two different elements in it, that's a binary compound. There's two different types of things in it that make up that compound. Okay. So I kind of explained that. Here's some examples of that. Sodium chloride. Again, it's an ionic salt. That's the most famous one we use on our food. Makes everything taste good. Sodium and chlorine come together in a 1-to-1 ratio because sodium has one electron to give. Chlorine, when it becomes chloride, takes that one electron, so it's a good match. Then you have aluminum oxide, Al2O3, and sodium oxide as well. Okay. Notice that there is just two different types of atoms or elements in there, and the ratios are different, but it's still, they're all binary compounds. Okay. And of course, it explains it right here. Anytime you have a binary ionic compound, it's got a metal and a non-metal in it. And just a reminder, whenever a metal gets a charge, that means it got oxidized, right? It let go of that electron or 2 or 3 electrons, however many it gets rid of. And then the non-metals, they get reduced. Okay. So keep that in mind. Okay. So here's the rules for naming binary compounds. There's always two words in it. The first word is the metal. It's unchanged. Whenever a metal gets oxidized, or it gets +1 or +2 or +3 charge, it's said to be oxidized. The name still is the same. Notice on those ones before, sodium chloride, right? Aluminum oxide. Aluminum doesn't change. The change happens on the non-metal. Okay. The second is the root of the non-metal with an IDE suffix. Okay, so it's not sodium chlorine, right? It's sodium chloride. So it's a subtle difference, which is part of those IUPAC rules that we're kind of shoving down your throat to get you to understand, right? There are no numeric prefixes unless the metal is a transition metal. Okay, if the transition metal has a different charge in it, then you're going to designate that charge with a Roman numeral in the name. Okay, and you can deduce that from the formula, and the more we do these, the more you practice it, the better you'll get. Okay, remember those transition metals in that area in your periodic table. Okay, so it's useful to know your Roman numerals from 1 to 5. Usually we'll just use 1 to 4, sometimes 5, but they're very basic, and it should be in this slideshow somewhere. Okay, so they give you an example. Titanium with oxygen, when it combines, titanium can have different oxidation numbers or different charges or different valence, whatever suits your understanding. And the reason why we know this is titanium 4 oxide is from the formula. Okay, because oxygen is always -2, and when you write out this formula, it reduces to 1 titanium for every 2 oxygen, and it's called titanium 4 oxide. Okay, because you could also have titanium 2 oxide, and that would be different. Okay, so we need to remember that any compounds must end up as a neutral molecule. All charges must be balanced. Otherwise, why would they come together and form a bond, right? So if I've got a +3 and you got a -3, we come together, that is a neutral number, right? They'll cancel each other out, and so it makes a nice little bond. So like aluminum and nitrogen, if they were to come together to make aluminum nitride, it's a 1-to-1, because a +3 will balance out a -3. So always watch that and make sure that those charges will balance out to 0. And it says, how can we find a formula of potassium sulfide? Well, we know that potassium is a group 1 metal. It's an alkali metal, and when it's got 1 electron in its valence shell, when it loses it, it will have a +1 charge, right? So sulfur, when it gets ready to react, it will take on 2 electrons because it has 6, right? So it has a -2 charge. So in order for this to balance out, you need 2 potassiums for every 1 sulfur to make potassium sulfide. Okay, and so more on that here in a second when I go over these examples with you. Okay, let's do barium oxide. So boom, I'm going to switch over real quick and show you how I can use your periodic table to solve this little problem here. The name of this compound is barium oxide. First of all, we check. Ooh, there's my metal. It's right there. It's an alkali earth metal, right? And it's got oxygen in it, and it's the nonmetal. So we know first and foremost, this is a binary ionic compound, okay? Because you have the metal and the nonmetal. So if I look at barium, when it gets oxidized, when it loses those 2 valence electrons, it will have a charge of +2, right? So I know I'll have barium with a +2 charge. And oxygen, when it gets reduced, it's called oxide, okay? And oxide will have a charge of -2, okay? Just like all of these nonmetals up to this little point right here, these 3 will have a -2 charge. Okay, so then I've got these 2 things. That's barium and oxygen makes barium oxide. Now we look, remember these 2 charges, they got to balance out. And this one's real simple because you got a +2 and a -2. You add those 2 together and they will balance out to 0, right? Because a +2 plus a -2 is going to equal 0. So it's just a 1-to-1. So basically, your formula then is just BaO. That's barium oxide, right? Write a little bit cleaner right here. Take your bow, right? All right, let's try another one. Something I forgot to mention is whenever you have charges that balance each other out, the ratio of barium to oxygen is 1-to-1. Okay, it's a 1-to-1 ratio. All right, here's an old shortcut that works, and you'll see this. If this doesn't work, you know, I'll show you a different way. But an old shortcut for doing these ionic compounds is you get the formula of a binary ionic compound is the crisscross rule. Okay, you simply just crisscross the charges or the numbers, not the charges, to get the ratio of potassium to sulfur in this particular little compound. So boom, I'll switch back to camera mode. So boom, here's the charges. Let me double check. Where's potassium? It's right here. Just like all the alkali metals, it's got a +1 charge. Sulfur is right under oxygen, and when it becomes sulfide, it has a -2 charge, okay? So that crisscross rule is you crisscross the numbers, not the charges, to find out the ratio. So I get this 2, boom, stick it down there. There's no 1 written here, but it's just understood. If it's got plus there, it's a +1. Just like if it was just a negative, it'd be -1. So boom, you bring that down here. You don't need to really write a 1 down because it's understood that there's 1. So when I do that, I get my formula, K2S, right? And then this is an ionic compound. Think back to those rules. The name of the metal doesn't change. So the name of this little ionic compound that you just created is potassium. Is it potassium sulfur? Remember, you got to change it to IDE, so it's potassium sulfide. Change it back. Bada boom, bada bing. That's using, the crisscross rule, which is real basic. But if that doesn't work, when you're doing this, you go, all right, well, there's a K plus there and an S2 minus, right? And I know when I add the charges, they have to equal 0, right? And so right now as it sits, a +1 and a -2 gives me -1. So how am I going to fix that? How do I remedy that? Well, I bring in another potassium right there. And if I add those 2 pluses, I get a 2 plus, and that plus a 2 minus will equal 0. Okay, that's the other way you can do it if the crisscross rule kind of hems you up and it messes you up. Okay, so let's take a look, see how they do it on the slideshow. You got the criss and the cross, bada boom, bada bang. And it says crisscross the absolute value. That's another way to do it. Don't bring down the charge, just the absolute value of the number. And then you put them as subscripts, and it's K2S. Again, it's called potassium sulfide. All right. Transition metals is a different thing. I'll make a quick little video on this. I'll cap this off at 12 minutes here, and then I'll pick up the rest of this here on a separate video so you guys aren't too bored. All right.